and we are given range left and right. We have to calculate the sum of the AVL trees values. The basic idea is AVL tree is self balancing tree, which is called BST. We can use it store structure to find the range sum faster than normal traversal. Like we have a BST 33, 9, 8, so 21, 11, 53, 61. The knife approach is, we can apply knife approach using pre-order traversal. Pre-order traverse, we are given L and R. The pseudocode is like to if root dot value greater than L, we have to update the total plus equal range sum root left L and R. If L greater than or equal to root value and less than or equal to right value, just only update the total value root value. If root value less than R, total plus equal, we call recursion sum root right L and right. Finally we return the total value. This is our naive approach. It works perfectly, but the problem is the time complexity of this algorithm is order of n. To update the AVL tree data structure, we now design an efficient approach which we called augmented AVL tree. Augmented AVL tree, where each node, like 33, each node will have value number 2 left right and number 3 height and number 4 is subtree sum, where each node subtree sum equal node dot value plus node dot left subtree sum plus node dot right subtree sum. This is our augmented algorithm, and its time complexity is order of log n, which is much faster than to order of m. In our machine learning model, ML model, we can use augmented and scalable approaches. Our scalable approach is only send changes from the affected subtree, number 1, and number 2 is collect multiple updates and send them together after some time, which we called batch update. Also we can use asynchronization and caching. So this is our first problem. Our question 2 is from B tree. So the basic idea, a B tree is a balanced search tree. That keeps data sorted and allows first search, insert and delete. In a B tree, all leaf nodes are the same level and data is stored in blocks that can hold multiple keys. Like we have a B tree 4, 2, 1, 3, 6 and 8, 5, 7 and 9, 10, 11. A B tree is a balanced search tree that keeps data stored and searching key. When search a key, its time complexity is only order of log n, which is very fast even for large data. Inserting new data, if we insert new data, then it does not require rebuild the tree. Rebuild the tree, no need to rebuild the tree. Database use B tree index data efficiently, so we can quickly find where a file or record is stored. When storing large model weight file, a B tree index help to database quickly locate which storage block hold a particular weight file or part of it without scanning everything. So now we can try it, apply in our recommender system. In recommender system, each user or item is represented by feature vector. To find similar user or item, like this one item, I1, item 1 and item 2, we can find out the similarity. The system often need to search and match vector first. So if we want to similarity, we need firstly vector match. Here B tree like indexing help us to quickly look up a user or item feature vector by ID or range. Quickly look up. Efficiently update the vector. Keep the search scalable even when the tree are million of users or item. So in this approach we can use B tree in our recommender system. Problem number 3. It is about MST, minimum spanning tree. Our one algorithm which is called GHH algorithm, which is famous method for finding AMST in a distributed system. Where data is spread across many nodes connected by communication link. Like data is communication link spread from one to one. So firstly we have to initialization is not start as an independent fragment. Is not every node start with an independent fragment. Finding minimum edges. We have to find the minimum edges. Minimum number of edges. Each fragment finds its minimum outgoing edge. Communication. Communication is meaning for purposing merging. Merging fragment. So we first have to initialization. Second is minimum edges have to find. And third point is communication. Fourth one is margin fragment. And we have to repeat all process like recursion. And finally termination. This is actually GSS algorithm work to find out the minimum spanning tree. It's work because it does not need a central coordinator. No need to central coordinator. Also nodes only communicate with nearby neighbor. One node communicate with only nearby neighbor. It works efficiently even when the network is large. If our network is huge, then also we can apply. Time complexity is order of n log n. In machine learning ML, MST are useful in cases where we need to find the most efficient structure or connection pattern among feature or data point, like one data point P1 and data point P2. We want to connect this point, and this is we call connection pattern. Then we need to MST. Examples, we can given an example like sensor network feature selection. Sensor, like it is a sensor and it is our network feature selection. From sensor we collect our feature. Suppose many sensor collect data, like this sensor may be temperature sensor and pressure sensor, and here we can collect data. We can represent sensor as node. This sensor we called node. And connection cost as distance. And connection cost, here the connection cost we called it distance. Using MST we can connect all sensor with the minimum total communication cost, avoiding redundant link. This saves energy and improves network efficiently, useful IoT or distributed ML. Here we can use MST. Also we can use other in clustering, feature selection, that we already discussed, and graph-based ML model. Graph-based ML model. So that's it. Question 4 is about slab connection and garbage collection. So slab allocation. Slab allocation is that memory is divided into fixed size of block, like this is 4 KB, it is 4 KB, and each segment or fragment we call slab. Each slab hold object. Here we can use data or object, and they are also same size like 4 KB, 4 KB, 4 KB. When one object is delete, then we can immediately other object to insert it. New object. No need for scanning or collecting garbage. Very efficient and predictable because allocation and deallocation happen in constant time, order of 1. The advantage of the slab allocation is low overhead because it is faster, no runtime pause, predictable latency, good for system in real requirements. The garbage collection is GC automatically find, like this is our memory block, automatically find and frees unused memory. Like this memory space is free, then it use automatically. It scan memory to detect which objects are no longer in use. It reduces programmer effort but causes unpredictable pause. Here apply unpredictable pause. Garbage collection cycle. Advantage is easier to deploy. Automatically manages memory. The main advantage is automatically manages memory. But it has limitation because unpredictable pause and memory overhead is high. In our ML system, avoid random GC pause. We use slab collection. Slab collection is best for our ML system because it avoids random garbage collection paths and ensure consistent response time when fetching or updating feature. In online ML system, fast and stable response time is critical, so slab allocation is preferred. As slab collection is fast and stable because it is not memory overhead of high and unpredictable pause. That's why fetching and updating feature is consistent in response time. That's why we use slab collection.